Good afternoon, everyone. Thank you for joining today's webinar, Addressing 911 Challenges 3D GIS Supporting Z-Axis. My name is Amy, and I'm the Operations Manager here at National States Geographic Information Council. If you are unfamiliar with our organization, NSGIC exists to advance effective national coordination of geospatial information by supporting state-level cooperation. We serve as a national forum, for the development of capable and future-oriented geospatial leadership. If you'd like to get to learn more about us, please visit our website, www.nishjic.org. Just some reminders for today. All attendees have been muted on intern. There will be some time at the end of the presentation for Q&A, so please place your questions into the chat box and they will be answered aloud. Additionally, a recorded version of this webinar will be made available afterwards, so be on the lookout for that as well. And with that, I will now turn it over to the presenter, Keith Owen. Keith?
All right, thank you, Amy. So good afternoon, everyone. My name is Keith Owens, and I'm the Commercial Director for Fugro. I've been with Fugro since 1996 in a variety of job descriptions, from being a sensor operator in the back of an aircraft to land survey, data production, project management, project estimating, to business development. And I'm excited to share with you our experience in connecting what we do in geodata collection and processing to how it's utilized for 911 dispatch. So this presentation is roughly 20 minutes in length, and we can open it up at the end for questions, should you have any. So a little bit about Fugro. So we're the world's leading geodata specialists, collecting and analyzing comprehensive information about the Earth and the structures built upon it. Through integrated data acquisition, analysis, and advice, we unlock insights from geodata to help our clients design, build, and operate their assets in a safe and sustainable and efficient manner. So we have operations spread across the globe with over 9,400 employees to support all things geodata. We believe understanding the Earth is key, and at Fugro, we unlock its secrets in the form of geodata, which we apply to develop safe, more sustainable, and more efficient operations. It's how we help create a safe and livable world together. So our geodata expertise in North America ranges from deep water and nearshore bathymetric surveys to geotechnical site investigations to online geospatial data acquisition and processing. Our production centers and office locations are spread across the U.S. from California to Maryland. Our remote sensing and mapping services include land survey, LiDAR, and imagery data acquisition, data processing, and product development. We perform these services through a variety of contracts with the U.S. GIS, the Army Corps of Engineers, NOAA, and a handful of state contracts like the Texas Department of Information Resources and the State of Utah Cooperative Contract, for example. So we can assist you in project planning, design, budget, and execution. Today, I'm going to share with you Fugro's experience addressing 911 challenges. In 2017, we started working with a very progressive and innovative GIS director by the name of Steve Kochis in rural Cambria County, Pennsylvania, to address their challenges with transitioning from a 2D to a 3D GIS. The project originated by Steve searching for a company to acquire oblique imagery to support their assessor department operations. And through conversations with the county, we've collaboratively built a program that would provide a countywide 3D model in addition to the oblique imagery to support not only the county assessors, but 911 dispatch and operations. Since then, we've been exploring all options for acquiring data to create 3D models, mostly to address 911 challenges. And this is supporting the Z-axis information that is now available from incoming cell phone callers. So with a mandate for cell phone or mobile carriers to provide the Z value in addition to the X and Y, we knew there would be the need for 3D data to support the geolocation information coming into the dispatch. We refined our solutions to support the upcoming need. Our goal was to utilize our expertise in geodata collection and processing, as well as product development, to improve situational awareness at the dispatch desktop. So this presentation will focus on two important topics: the options for creating 3D data and the interaction of that data at the 911 call center. So there are more ways than one to create 3D models. From this presentation, we'll focus on 3 aerial data methods: acquiring LiDAR data and creating untextured 3D building models, as shown here, utilizing only nadir imagery and concurrent LiDAR, and using oblique imagery. Each have their pros and cons. The LiDAR-derived 3D models are vertically accurate, but lack building texture. Nadir imagery, looking straight down, with concurrent LiDAR, produces vertically accurate textured 3D data, but can sometimes lack details on some of the facades. And oblique imagery produces visually appealing models, but can oftentimes seem post-apocalyptic or lack positional accuracy. So I'd like to dive into the specifics of each method, but first with the LiDAR-derived building models. So LiDAR data is widely used to support a variety of applications throughout the country. The USGS 3DEP program is likely the most common source for LiDAR data, but can sometimes lack classifications to support the creation of building models. So we tackled this problem by developing a technique for accessing that available LiDAR data and classifying that to a high degree of accuracy. The USGS 3DEP program is providing excellent quality LiDAR data throughout the country. When using this current data, we're able to add classifications to increase the use case. Common use cases for LiDAR data include a DEM creation, hydro studies, flood analysis, and contours. And today, with the advancements of LiDAR, we're expanding that use case to include vegetation analysis, building models, and asset inventory. We deploy Fugro's AI and machine learning techniques to classify the point cloud for identifying the buildings in this case. An important thing to consider is with the older LiDAR data sets, those weren't held to the same standards as they are today. So that data could oftentimes miss details in the buildings due to sensor settings, collection parameters, and post-processing methods. In this example, settings at the data capture impacted the LiDAR point's ability to pick up certain building features and oftentimes miss details in the vegetation. To work around the data voids, we use human interaction to help identify the buildings missed from the antiquated data. So since LiDAR, the machine learning technique, is created by Fugro for deploying the cloud-based processing using the AI and machine learning to classify clusters of LiDAR points over large areas at a high degree of accuracy. Deploying the machine learning techniques, we take new or existing USGS LiDAR data and add classifications like low, medium, and high vegetation, buildings, and culverts. This is in addition to the already classified bare earth, water, bridge decks, and high noise and low noise. So this is a top-down view of an example area in northern Texas. This graphic shows our ability to classify the trees against the buildings. And when we remove the vegetation and the unclassified, you can see we're accurately defining the building details even when buildings intersect with vegetation. So if I switch between the two, you can see here that we're able to identify even when buildings are over top of trees are over tops of the buildings, we can easily segment out those buildings to help us with the creation of building footprints. So with the more accurately defined buildings, we can create automated building footprints. And we've been successful in generating these building footprints in the subsequent models from the LiDAR data set as coarse as 2 points per square meter. The 2 points per square meter LiDAR data provides enough detail to create the building model, but could lack details like roof slope or roof assets like an air conditioning unit. It's important to note that LiDAR-derived building models are not textured, so details like windows and doors on the facades of these buildings will not be visible without the help of imagery. However, we feel the data is good enough to provide building models at an affordable rate over areas of the country that may not require the details typically associated with fully textured 3D models. Our goal is to utilize as much available data as possible to help rural communities transition to a 3D GIS. As the LiDAR point densities increase, you can see we're able to get a bit more refined with our building model output. There are subtle differences between the 2 points per square meter, and in this case, 4 points per square meter, but this showcases the importance of increased density and its ability to capture more details when generating LiDAR-derived building models. We're able to capture roof details a little bit better. Roof slope is better defined, and we even start to pick up roof assets. As the density increases, so does the quality of the building itself. Progressing to the method of combining aerial imagery and LiDAR, we've explored techniques for using only nadir imagery and high-density LiDAR to support texture 3D model creation. We feel by combining the LiDAR and imagery, we're capturing the best of both worlds in terms of accuracy and detail. We're using the vertically accurate LiDAR data, typically better than 10 centimeters RMSE, with horizontally accurate imagery, which would be an ASPRS class for the resolution it's collected at. And this creates a well-rounded geodata package for all things 3D modeling and expanding use case to support a variety of GIS-related programs. This example showcases a project in Malibu, California. This is where we were tasked with creating a 3D model of Pepperdine University using nadir imagery and LiDAR data in concurrent. The project was captured at 2-inch pixel resolution, and we utilized 30 points per square meter LiDAR data to support the development of the 3D model. We used our machine learning techniques to classify the LiDAR point cloud and photomesh software to create the 3D model. This is a show of the true ortho derived from the production routines. I wanted to point out that we typically use the center area of an image to create an ortho, but in this case, we use the entire image, including the outer edges normally thrown away in the ortho process to assist with feature texturing. The fully textured 3D model using aerial data provides enough detail to allow university to make operational decisions at the desktop. The 3D GIS displays a geolocation of roof asset information, assets on the ground, and their connections to the natural environment. So by using vertically accurate LiDAR data and horizontally accurate imagery, the users of this data can perform precise measurements from the data and have confidence the data is their single point of truth for future projects and data collection efforts, something like drone collections for adding in details in the future. But while I love highlighting the accuracy of this method, it's important to showcase some of the imperfections. In this case, since we're only using nadir imagery, we oftentimes lose some details in the facades. Details start to be reduced when there are a few looks at an object as a result of the flight line side lap and overlap used when acquiring the data. But while those imperfections can be easily showcased, it was more important to this user to have details in the urban canyons typically obscured from a photo-only technique like oblique imagery, discussed a little bit later on. The aerial LiDAR capture concurrently with the imagery does provide nice flat roads and details under tree cover as compared to the imagery-only approach as well, something important to note. But we feel the pros outweigh the cons in this method. We're able to utilize 2 common data products to generate a 3D model to help improve situational awareness and operational decisions. The data captured for this method are commonly used for other purposes like contour development, orthoimagery for their base map, LiDAR for vegetation analysis, flood simulation, slope analysis, and cross sections. So our third options for generating aerial derived 3D models is the aerial oblique imagery. We've been capturing oblique imagery for many years, and this was our start at generating 3D models dating back to 2017 for Cambria County, Pennsylvania, as mentioned earlier. The oblique imagery derived 3D models use all of the images, including the north view, the east, the south, the west, and the nadir view from the oblique camera system to create the photo-derived 3D model. The oblique imagery can range in resolution. Here's an example of 1-inch oblique showing the details of the side of a building. But it's more common for wide area collections to range from 2 to 6-inch pixel resolutions. Here you can see from the 3-inch imagery, you're able to capture details on the facades of the buildings like window locations, doors, and various assets. But as you fly higher, the resolution gets a bit coarse. You can still pick out some of the detail in the windows and the doors locations, but you may start to lose details in various assets. Keep in mind, the higher you fly, the lower the resolution, and the lower the resolution, the lower the data size, resulting in lower cost of operations and data production. The oblique imagery derived 3D model project have great cross-department use cases and provide great detail in the facades. But I'd like to point out project flight planning is very important, and this influences the quality of that 3D model. For example, for Cambria County, we increased the side lap and the overlap of the flight lines compared to a traditional oblique imagery project, a project that wouldn't require the generation of 3D models. And the increase in overlap and side lap of the imagery allows for more looks at objects on the ground, helping to improve the quality of the 3D model during the data production. For this project example, it's important for Cambria to use the oblique imagery to support their assessors in a 3D model to assist with a variety of activities, one being the enhancing the GIS at the 911 dispatch. It is possible to generate 3D models from standard side lap. However, subtle imperfections start to surface, which could lower user confidence in the data. It's important to consider how data is acquired and the impact planning has on quality and accuracy. The higher the resolution, the better the detail. However, the higher the resolution requires us to fly lower, requiring more flight lines, more ground control points, and process more points and pixels. But regardless of the resolution, standard mapping projects typically only require about 20 to 30% side lap and 60% overlap in imagery. But when creating 3D models, we need to increase that overlap to allow more looks at an object on the ground to help improve the quality of the model. And this adds flight lines as compared to a traditional project, which ultimately adds time and cost to the project. But when using standard overlaps, you lose details at the ground level. Often the data can seem a bit post-apocalyptic or melty, and this can cause the user to lose a bit of confidence in the data. We also see areas with wavy features or added noise, or missing parts of the buildings caused by window reflections. All of these can be remedied by human interaction and, of course, post-production fixes. But good to know when designing your project, it's important to keep in mind how we plan these things to get the best outcome. But in conclusion, many rural communities like the cost effectiveness and vertical accuracy from the widely available public LiDAR data for generating the untextured 3D models. Cities typically like the vertical and horizontal accuracy of the LiDAR and NADAR imagery approach to create the textured 3D models. And the availability of the source data, the high density LiDAR, the high resolution imagery is used across many city departments in addition to the 3D model itself. And it is common for counties to have oblique imagery flown for their assessor departments. In these cases, that data can be used, but may lack the enhanced project planning necessary to generate a quality 3D model. So I'll now dive into how 3D data is used at the emergency call center. So we realize most people do not like to install new software or interrupt an already invested in process for managing GIS. So we found it important to connect with systems that were already installed. Our first integration was with RapidSOS. RapidSOS does well with receiving the cell phone call or geolocation information, but may lack interaction with the Z value in 3D. So Fugro created a patent-pending plugin that made it easy for dispatchers to interact with the 3D data without requiring a lot of training. A 2 or 3 click method for interacting with a 3D world and performing simple functions for measuring or gathering details about the area of interest. The geolocation of the caller is placed in their transmitted location in 3D, and that's to assist first responders in locating them and directing people on the ground to that location, improving the response times. We created the Symmetry plugin so dispatchers had a variety of functionality to support their daily operations. This was to help improve their situational awareness and improve their communications to first responders on the ground, assisting with the emergency services. The Symmetry plugin connects to a wide variety of GIS data sources and burns the detail into the 3D model. This allows for simple functions like identifying an address by clicking on the feature, or to query or to search addresses, and even bookmark the location to revisit as necessary. Here we're displaying road center lines and their labels for identifying something as simple as road intersections. And here we're accessing building information by connecting the building footprint attribute data and accessing it through the attribute inspector within the software itself. Attribute information is obviously user defined, of course. It could be as something as maybe simple as the feature ID itself or contact information for the building or parcel owner. Users can further expand their interaction with the 3D data by performing quick measurements for horizontal and vertical distances and areas on the ground, rooftops, and facades of the buildings. This is a benefit of using 3D data to perform quick measurements. We're even adding in functionality, for example, a building collapse zone for identifying hazard areas during something like a building fire. This video showcases how functionality can be modified to support unique situations. In this case, I was listening to the news one morning and a fire chief was speaking about a tall building fire they had responded to. The fire chief mentioned he needed to create a collapse zone around the building equaling 1.5 times the height of the building for identifying areas of potential impact if the building had collapsed. After that, I spoke with other 911 directors regarding this issue, and they mentioned this calculation could take some time to create. So we collaborated with our development team, and in just 1 week, we added the functionality. So expanding on the collapse zone, we created a safety zone. The safety zone tool allows the user to place in user-defined distances from an instance to identify areas for something like closing streets, parking service vehicles, or alerting the community of potential hazards. These are all very quick functionalities within the systems. All of these things we're adding in, they have to be very fast, 1 or 2 click or 3 click items and perform very quick response times and results. The safety zone tool is not limited to buildings. These can be used for vehicle routes like a parade or a community event like a 5K run. But likely one of the most important functionalities of the 3D GIS is our ability to turn the 3D world into an X-ray vision. This allows us to gain access to the interior details of the building. By clicking on Building Explorer, users can identify the caller location against available floor plans. And when floor plans don't exist, we can estimate floor number and caller location on the floor. Other details like fire extinguisher or defibrillators locations can be placed on the floor plans to assist with the emergency response. So this concludes my 20-minute presentation and our showcase of our efforts in addressing 911 challenges. I would like to thank you all for attending the session. My contact information is located here. You can use the QR code to connect with me on LinkedIn, or you can email me directly at k.owens@fugro.com. Hope you enjoyed the quick presentation, of course, but if you do have any questions, I think now might be the time to open it up for that.
Thank you, Keith, for that wonderful presentation. Like you stated, please feel free to put in the chat your questions and they'll be read aloud right now.
Doesn't look like any questions are coming in. Clear presentation.
And Keith, would it be okay if we shared the presentation as well with the recording, or would
Presentation size a bit large before you know, for displaying online because of the videos, but happy to create a shareable versions.
And we did get one question. What CAD systems have you worked with?
So we were with this one here, because of the cell phone coming in, we're using the Rapid SOS for integration, and which is kind of in addition to the CAD systems. The CAD systems being a landline, I believe, and if I'm not mistaken, it might be called Infor, but I'd have to get some details on the landlines solutions as well. When we do deal with landlines and we're not receiving a cell phone call, the geolocation of that person's information is associated with the address of the landline call itself. versus the cell phone geolocation and XYZ.
We got another one. How do you handle buildings built after USGS LiDAR? How does it get added?
Sure, sure. A lot of times, we try to use as much of the existing LiDAR data as possible from USGS's one, and state and local collections might be a little bit more current in some areas. But where not, some of our clients are actually deploying drones or other data collection methods to create a building model to be added into the model itself. In certain cases, we will use a built-in footprint and a generalized height based off of other methods of kind of identifying those features after something like a USGS LiDAR collect. So there are ways to manipulate the data to get a bit more current, but obviously the source data itself has to exist. So whether it be a new collection of new LiDAR data or a new collection of LiDAR and imagery, which we can certainly help with, or adding in things like a drone collection of a site-specific area itself, or collecting the building footprint and adding a height to it.
Can your data be used in Esri products?
Almost certainly. All the data we deliver is industry standard. So everything, we want it to be used regardless of the platform itself. So it's important for this data to be used in pretty much anything that exists in the GIS industry. Thank you for the question, Howard, Christian, and compliment Frank.
And another question was asked, can drone models and imagery be added in?
Oh, it certainly can. So our buddy there at Steve at Cambria County, I assume, was asking this question. Yes, he's doing that quite often at the moment, where he'll go out and do added captures and add the data in as necessary. That's kind of the benefits of managing a 3D mesh. You do the initial collection, the wide area collection, usually with the human or crewed aircraft. Then as time goes on and you have areas of development, you can deploy drones to capture details in a similar fashion using the same coordinate system to make sure that the data fits in with the existing data. And then you can patchwork that data in. It does require a little bit of post-processing technique and making sure that the data aligns with the base information that we create. But that's extremely important for us when we're creating that base information, that you use industry techniques to make sure it's accurate and complete. The accuracy of that base information really impacts the further collection of site-specific areas and your ability to add those other areas in. So in this case, accuracy certainly matters. Any additional questions?
Well, Keith, it seems like this presentation we did get one more. What about underground?
Underground, yes. Another benefit of 3D data. A lot of these buildings actually have basements to them. So when you enter into the immersive kind of world of 3D data, that's the benefit of that, is that you can bring in other sources like borehole information, geotechnical layers, underground assets like underground utilities, if they exist. You can put them in their true Z value underground. One memory that comes to play is I was speaking with a 911 director in the Gulf region, and they were talking about a building collapse that happened in their city, and a crane of the building punctured the ground, and they were doing an emergency services response to that crane puncturing the ground. And they said one of their biggest challenges was determining what kind of asset existed under the ground where that crane had punctured. In the 2D environment, it was difficult for them to maintain, all of those assets and understand the depth in which those assets were kept. But by transitioning into a 3D world, you're not held to just the above ground assets, of course. It's a globe essentially, so you can manage assets, 5, 10, 20 feet underground, just as well as the assets that are 100, or in this case, 662 feet above ground. So, one thing to kind of mention here as we close out, this is, important to consider. And one thing I maybe didn't tap into in the presentation here was managing all of this data. For us to capture large areas, oftentimes we're measuring data in the terabytes, if not petabytes, depending on the size of the project we're working in. The data can be hosted online. It could be accessible at the location. So what we've done is we've built a system to allow the people to interact with this data regardless of the location itself. We can ease the burden of data management by hosting this in some reliable servers like AWS. Or we can give you access to all the data we collect. You own it, not us. So that data can be stored at your location to be functional when, let's say, the internet goes down. So very important point I maybe failed to mention earlier in the presentation.
Don't see any additional questions, but if anyone would like to put in any last minute, please do.
Yeah. Well, I certainly appreciate the opportunity, Amy, for you allowing us to come on and showcase this. We hope that people found it worth their time. Again, my contact information is listed there. And really look forward to you guys reaching out and further kind of exploring ways to improve the way we interact with 3D data. So I thank everybody for their time.
Yeah, and thank you, Keith, for coming on and giving this very informative and visual presentation. I really enjoyed the demos, and I am sure the audience did as well. So, any last words or?
No, for me, it was great to speak with everyone. I appreciated the questions. It's always nice to have a little bit of back and forth at the end. Thank you all very much.
Yeah, and thank you, Keith. And just a reminder, folks, this will be recorded and distributed for your later convenience as well. And thank you to the audience for joining us. And thank you again, Keith, for coming on and bringing this awesome presentation to NSGIC.
No, it's my pleasure.
Okay. Have a good afternoon, everyone. We'll give you some time back.
Bye, everybody.